A disk of mass m is at rest inside of a square box tilted at an angle theta with respect to the ground. The disk is in contact with two sides of the box as shown in the diagram. Find any forces acting on the disk. So, in this question we're dealing with a static case. These two black lines, these thick black lines are our box, our square box. This is obviously the disk. And here's the angle theta. And we want to know any forces acting on this disk. So the first thing we want to do in a question like this is to draw a free body diagram. We want to draw any forces that we think should come into play. And we're going to treat this disk. We know that this disk has obviously got some size depending on the radius, but we're going to treat it like a point particle of mass m located at the center of mass of the disk. And the center of mass of a disk is just the geometric center. So it's this red dot here. In other words, any forces that are acting on any point of the disk here, we can just treat them as though they were acting on a point particle of mass m located here. Now, the first force that we can list is obviously going to be gravity. We know that the disk is some height above the ground, and we know that gravity points straight down. So we should have one force vector that goes from here and points straight down that we can call F gravity or mg. In addition, we note that the disk is in contact with the box at 2 points. It's in contact with the box here and here. So let's label those points. Here we have point P1 and point P2, the contact points. And we know, for example, that the disk will be pushing on the box. It will be pushing on P2 in this direction, and the box will be pushing back with an equal magnitude in the opposite direction. This is just Newton's third law. For every force, there's an equal and opposite force. So now we add two new force vectors. Let's label them N1 and N2, and we'll add that to this point here. And again, N2 is just the force vector that you get from drawing a straight line from the contact point here, and N1 from this point. So these are the only forces at play. There's no friction, presumably, since the question doesn't state there's any friction or any other forces. And no matter what coordinate system we use, the forces should look like this. They'll be pointing in these directions and have these magnitudes. The issue is, how do you measure these forces? What coordinate system will we use to describe these forces? And the answer is we can use any coordinate system we want. So for example, we could just choose regular Cartesian coordinates, where the horizontal line is the x-axis and the vertical line is the y-axis. So here we have, let's say this is the x-axis and this is the y-axis. And then all we would have to do is we would have to break up each of these force vectors into its components along the x-axis and the y-axis. We're only dealing in a two-dimensional case here. So mg, we can see it only points straight along the y-axis. It has no component horizontally. On the other hand, n1 and n2, we can see that they're not aligned with these, with the red axes. So n1, for example, will have some component horizontally and some component vertically, and likewise for n2. So if we choose this regular Cartesian coordinates as our coordinate system, we'll have one component for mg, 2 for n1, and 2 for n2. But since we can choose any coordinate system we want, we could have chosen this system or polar coordinates or anything else, we may as well rotate these red lines so that they align with n1 and n2. So we can rotate this as so. And why do we know that they're aligned with n1 and n2? Because the question says we have a square box, meaning that this side and this side are perpendicular to each other. And obviously the normal forces are perpendicular to these sides, so N2 is perpendicular to this side, N1 is perpendicular to this side, and so N1 and N2 must also be perpendicular to each other. And as you can probably figure, this is useful because now N1 and N2 both only have one component along each of these axes. We'll call this the x-axis and this the y-axis. And mg now has two components, but we've still simplified things a little bit. If you wanted to just work with regular Cartesian coordinates, this being along the horizontal direction, you can, there's no problem. This is just to save a little bit of work. So now let's just break up mg, the force due to gravity, into its components along this axis and this axis. Again, this is the x-axis, this is the y-axis. And so the components should look like this. We have, let me remove the red axis so you can see better. We have one component in this direction and one component in this direction. And actually, let me also remove this vector. So again, when you add these two vectors, you get the original gravity vector. Now, we know that the whole system is at rest. We're dealing with a static case, meaning that this force mgx has to equal in magnitude n1, but their opposite direction. And likewise, mgy has to equal n2 in magnitude, and obviously opposite direction. So what is the force N1 in terms of the gravitational force mg? Let me add this force vector back. And I'll tell you the answer is N1 equals mg times sine theta, where theta is this angle between mg and mgy, which happens to be the same as this angle here, the angle between the box and the ground, the angle at which the box is tilted. And first of all, you should convince yourself, if you're not already convinced, that this actually is the answer, because for example, if you move mgx over here, which is just vector addition, then you'll see that the sine of this angle equals mgx over mg, and so mgx simply equals mg times sine theta. Now we want to find N2 in terms of mgy or mg, and again, it's using the same idea as before. Obviously, all we have to do is switch the sines with the cosines. So N2 equals mg cosine theta. And once again, this makes sense because here, cosine of this angle here is mgy over mg. So mg, or mgy, is just mg cosine theta. By the way, if you're not exactly sure why this angle equals this angle, then first of all, you should be able to get to the result pretty easily. All you have to do is play around with the geometry of the problem and draw some lines going through here or here and use some trig identities. But you can also just use a logic check, because right now the box is tilted at an angle, but let's imagine that it was more or less horizontal. So here we have the box is almost tilted at 0 degrees, and we know that sine of 0, or sine of a very small angle at least, is approximately 0, and so N1 should disappear, and indeed N1 is almost gone, while N2 is approximately mg cosine of 0, which is approximately mg, because cosine of 0 is just 1. In other words, N2 is, let's actually move the box to be completely flat, and now N2 is just mg. The magnitude N2 is just equal to mg, which is what we'd expect because the object is flat on the ground. On the other hand, there's no other horizontal force, and mg times sine of theta is equal to 0. So again, if you started off here and you weren't sure what angle this should be, then you can just first look at the extreme cases, and that should tell you that this angle should be equal to mg when cosine theta is equal to 0. That's going to do it for this problem. Hopefully it wasn't anything too challenging. If anything didn't make sense, then I would suggest watching it again. And with that, we can actually move on to the next problem.